Greetings, globeheads and flurfers. You know, one of the topics that flat earthers have been talking about a lot lately is the question of centrifugal force on a spinning globe and what its effects would be. And there seems to be an awful lot of misunderstanding among flat earthers about centrifugal force and how it works and about just how fast the earth is spinning. I have said this before, and I've heard other debunkers say it as well. The earth is spinning half the speed of the hour hand on your clock. The hour hand on your clock makes 2 complete revolutions every day, and the earth makes just 1. Now, if I would put this in terms of RPMs, rounds per minute, which is how we usually describe things spinning, the Earth is spinning something like 0.000694 RPMs. As a comparison, I don't know, many of you might be too young to remember, but record players used to play an LP at 33 RPMs, and the smaller singles used to play at 45 RPMs, and there were some old records that used to play at 78 RPMs. So if you think of this in terms of a record album, LP we called it, 33 rounds per minute, compared to the Earth at 0.00069,444 RPMs. That is incredibly slow. 1 revolution per day. Now, as you know, things that spin incredibly slow do not generate a lot of centrifugal force. The flat earthers always emphasize ground speed at the equator. The Earth spins at 1,024 miles an hour or something like that at the equator, and yes, that is fast, but that's not the whole story. Linear speed at the outside of the circumference of the circle is not the only thing that goes into a centrifugal force equation. So what is centrifugal force? First of all, centrifugal force is what we call a fictional force, meaning that, scientifically speaking, there's no such thing as centrifugal force. Now, what do I mean by that? It's not an actual force. We can see the effects of centrifugal force, but there's no actual centrifugal force. The force we're talking about here is called inertia, and this falls under the first law of motion, which is that things that are at rest tend to stay at rest, and things that are in motion tend to stay at motion. Well, when something is in motion, what it wants to do, and I use that term want loosely before some flat earther comes along and says that accuses me of claiming these inanimate objects in space or whatever are sentient. Well, I don't mean this literally, but things that go in a straight line, they want to continue going in a straight line. Physics says motion wants to continue on that same path. We call that inertia. So if you are on the surface, the lateral surface of a circle, and you are traveling, your mass tends to want to go straight, but if you're traveling around that circle, there's a change in direction. We call that acceleration. So this centrifugal force is simply the inertia of the mass trying to go straight when it's being pulled in a circle by whatever other intervening force. Now, if you look at it as simply the lateral speed at the equator when you're talking about the Earth, you're ignoring the fact that it's very important to how strong this force is going to be, just how much you are turning. And as you could imagine, the bigger a circle, the closer to a straight line objects are moving in. Think of it this way. I live in Houston. I don't know how familiar you are with Houston, but whatever big, large city is near you probably has a similar situation. In Houston, we have what we call a beltway. The actual name of it is um, Highway 8, and it's a toll road. It's called the Sam Houston Toll Road also as well. Um, but everybody just refers to it as the Beltway. The entire distance around the Beltway is massive. It's something probably approaching 100 miles. I don't know. I should have looked it up tonight. I didn't. But it literally goes all the way around the city. Now, you could theoretically now, don't try this. You could drive around the Beltway all the way around at 90 to 100 miles an hour. Now, again, I'm not recommending anybody do that. I believe the speed limit is like 65. You will get caught. You will get a ticket. Don't do it. But in theory, you could do this, and provided there's no heavy traffic or anything like that, you're probably going to stay on your wheels, and you're going to make it around this, even though you're turning in a circle most of the time. Now, in theory, and don't try this, if you were to go to a parking lot and try to take that same speed, turning in a very small circle around that parking lot, you would either slide out, spin out, flip over. Something would go horribly wrong. Everybody knows you can't go certain speeds depending on how tight the circle is. And the tighter the circle is, the slower you need to go around the circle. This is why we have signs on the freeway that say, this corner coming up is sharp, and it warns you don't go over a certain speed, especially for semi-trucks and things that have a lot of mass. So obviously, the tightness of the circle is part of this calculation of just how strong this fictional force of centrifugal force is. And here's what you need to understand: as you make the circle smaller, the surface speed decreases, even though the rotational speed stays the same. Let's go back to the hour hand on the clock. The hour hand on the clock moves so slow that you cannot see it move. And yet, it's twice the speed of the spin of the Earth. So, what if you were to take that hour hand and you were to make it the same length as the radius of the Earth, which I believe is something like 8,000 kilometers? Well, the end of that hour hand would be moving 2,000 miles an hour, twice the speed of the spin of the Earth. And guess what? It would have no more centrifugal force on it than it does now, being short. Because at the very end of it, even though it was moving that fast, its change in direction would be so much smaller on a circle that big. See, this is not difficult stuff to understand. So when you hear people talk about how the Earth is spinning and how things should be tossed off the Earth, that's nonsense. The Earth is spinning extremely slow. Now, every spin does create some centrifugal force, and you will find this on the Earth. You will find that you weigh a very, very, very small fraction less on the equator than you do at the North Pole. It's like, I can't remember if it's 3 pounds or 0.3 pounds, but it's a very, very small amount of difference. Now, I actually got into an argument with Mr. Pratt today because he He tried to claim that I was saying if you're 3 pounds lighter on the equator, that I was saying that there was a 3-pound force pulling you up at the equator, so therefore water should fly off it shouldn't take more than 3 pounds of force for water to fly off. You have to think of all these things in terms of how they balance each other out. So take your weight. Let's say I weigh 200 pounds at the North Pole, and I weigh 197 pounds at the equator. I wish I weighed 200, but I digress. That doesn't mean there's 3 pounds pulling up on me at the equator. In the sum of things, there's 197 pounds pulling down on me. It's just less because of that centrifugal force. But still, the predominant force there is gravity. Yes, the Earth bulges out at the equator. Not because something is literally pulling it up, but because between the balance of gravity versus the centrifugal force, there's a less strength of gravity pulling it down in the end. And so things don't condense down as much. It's that simple. It's not a matter of enough centrifugal force that it's going to overcome gravity and it's going to spin things off into space. That's ridiculous. And oh, by the way, when you get a ball wet and then you spin it on your little videos to show that water will not stay on a ball, that water isn't going to stay on that ball anyway, because that ball is, that ball is so much smaller than the Earth you're standing on, and the gravity doesn't even compare. The gravity of the Earth you're standing on is ultimately going to be what pulls that water off that ball anyway, if you're not spinning it. And the only way your experiment would make any sense whatsoever is if you were doing it in space. And actually, you can find videos on the net of a guy in a spaceship in the space station wringing out a washcloth, and the water stays right there on his hands because it's attracted to his mass. Even though it squeezes out of the washcloth, it doesn't go anywhere. And that's what would happen with your ball. If you could do your experiment in space, the water would stay on your ball. But it's not going to happen on the Earth, because if you're on a ball that weighs something like 5.69 times 10 to the 24th power kilograms, this ball we call the Earth, and it is the dominant gravitational force. You're not going to get liquids to stay on anything on Earth when they're going to be trying to get down to that Earth. This stuff isn't rocket science, folks. Please hit like and subscribe, and don't fall for the snake oil salesman out there.